Hi everyone, welcome back to Intro to Modern AI. Today we're going to talk about self-attention. And self-attention really is the core operation of what's called the transformer architecture, which we'll cover more next time. But this architecture, and hence self-attention, really forms the basis for modern large language models. And in doing so, it really kind of is, in some sense, one of the most important operations of modern AI models. So today we're going to first, in particular, talk about the LLM setting again. We're kind of going to set this up, kind of what our inputs to the self-attention operator are, kind of corresponding to different words in the input sequence. We're then going to talk about the self-attention operation. We're going to define what this means. We're going to actually show a simple implementation of it. And we're going to basically talk about kind of how this operation mixes together different components of the input. We will then talk about the interpretation of self-attention as a soft lookup table. So a soft lookup table interpretation. And this is often how oops, I keep misspelling that. As I was saying, this is often how self-attention is described kind of intuitively. And I'm going to talk about this, but I'm also going to talk about the limitations of this interpretation, because I think while it's good to sort of be aware of how to interpret self-attention as this soft lookup table, it also has some significant limitations, and I want to emphasize kind of how this approach also can be limited. Finally, I'll talk about some properties of self-attention. And in particular here, I'm going to talk about how self-attention is invariant to reorderings of the data. The actual technical term is equivariance, but we'll just think about it as it doesn't really matter if you reorder elements of the input. The output will just be a similar reordering of the original outputs. And we'll also talk about the fact that it kind of mixes over the entire set of inputs that it's given. And then finally, we will talk about multi-head attention. And this, I'm capitalizing some of these. Attention. Multi-head attention is a slight extension to self-attention that has a bit richer of a mixing over the different input elements. And this is the actual operation that people typically use in transformers. And so we'll define what that is and kind of look at the details of that operation. All right, so before we begin, let's just start by recapping the LLM setting. Kind of in the simplest case, we will dive more into this next lecture when we talk about transformers as a whole. But to recap briefly, in the LLM setting, we had inputs which were sort of words, which were sequences of text, like the quick brown. And the output was the next word in the sentence. So in this case, fox, right? And the goal was sort of to map from this, to build a model that maps from this input to this output. And remember, the way we did that was we formed this input matrix, and this input matrix, we sort of formed this one hot, I'll call it, so that's OH there. And this was an input matrix that sort of, in this case, would have 3 rows, so I'll draw the rows a little bit shorter. We'd have 3 rows and a whole lot of columns, where this first row here, so I'll call this X1 transpose, this corresponded in some way really to a one-hot encoding of the word the. Maybe I'll annotate that with a different, annotate that with a different color here. So this first word corresponded to the word the. The next column corresponded, of course, to the word quick. And in particular, we would use what we called this one-hot encoding to encode these things. and this would be the word quick, etc. And the next one would be the word brown. And each column in this matrix, of course, I'll just write the last one too. This would be x3 transpose. Not each column, each row in this matrix corresponded to kind of one of these words. Now, the first thing we did kind of in our model that we talked about before is we would form what's called an embedding representation of this input. So we would essentially form our input that we actually use to the rest of the network as some linear function of this. So it would be x1 hot here times, say, an embedding matrix. And you can go back to look at kind of the details of how this actually worked from last time. But basically, if this matrix here was, in this case, t by the size of our vocabulary, t by v, I think I just called it actually big V, t by v, then this matrix here would be, well, I guess after the transpose, it would be v by little d, where d is the dimension, but the sort of the dimension of the embedding that we're going to use throughout the network. But really, the important part here is that we have, in general, this matrix X here. And in general, X is a matrix, so we sort of thought in general as X being a matrix which was T by D, where T was the number of words in the input, and D was some embedding dimension, some sort of hidden dimension. And throughout this entire network, we can think of this representation as kind of having each row corresponding to an input. So each row still in this other matrix here, I guess I'll even just write it out here. Let me move it down. So we can still think of this thing as being equal to some number of rows, the first row being x1, transpose, etc., all the way down to xt transpose. And we still have this sort of property here that the first row corresponds to the first word in the input, and each row, this second row corresponds to the second word, etc., all the way down to the last word in the sequence. So this, in some sense, is this representation that we're going to manipulate throughout our operation. Now, what self-attention is self-attention is a way of mixing together information across the different components, across the different rows of this matrix. So remember last time we talked about kind of there being two core elements of these structured input models. There were left multiplications, so there was some term like this. Basically, we could multiply this matrix X on the left by matrix A. Actually, let me write that in a different color. And multiply it by a matrix A on the left, and that would mix together different columns. We could also multiply it by a matrix W on the right, and that would, A on the left would mix together different rows. W on the right would not mix together different rows. It would apply a separate operation to each row in the matrix. And what self-attention is going to be is self-attention is going to be a particular instantiation of kind of a mixing operation like this. So let's jump in then and just sort of define what self-attention is. So I'm going to define now the self-attention operation. Okay. So self-attention is going to be an operation that takes as input our matrix X. That's going to be, again, a matrix in which is going to be T by D dimensional. And it's going to output Y. I'm going to write this sort of as Y equals self-attention applied to X. But I'm actually not going to quite write it this way. What I'm actually going to do is define self-attention in two steps. So the first thing I'm going to do is define three matrices, which we're going to refer to as queries, keys, and values. And these are all just going to be linear operations applied to this matrix X. So we're going to form three matrices. and these are called Q, K, and V for queries, keys, and values. And these are all going to be the same size as X. They're going to be T by D. And in particular, what we're going to have here is we're going to have three separate linear operations applied to X that generate these three matrices. Okay, so we're going to have Q equals X times one matrix. I'm going to call it WQ. K equals X times WK transpose. Again, we're just using our notation of linear operations being multiplied by the transpose. And V equals X times WV transpose, where here all of these three matrices make things the same. They take a matrix that is T by D, i.e. X, and transform it to another matrix that is T by D. So that means that all of these matrices, WQ, WK, and WV are all just D by D matrices. So that's sort of the first step of self-attention. The next step is that we form kind of the canonical self-attention operation. And here's what it is. So then we'll just say we'll output the self-attention operation. And here we will actually define self-attention, y equals self-attention, not in terms of X, but in terms of these three elements, W, K, and V. Sorry, Q, K, and V. Q, K, and V. And this is just going to be equal to the following formula. And this is the self-attention formula. It's going to be equal to the softmax. So I'll define what that is in a second again. Remember, softmax, I'll recap what that is. Softmax is an operation that exponentiates the individual elements and then divides by their sum. But it's going to be the softmax of what's going to be Q times K transpose over the square root of D. D here is just this dimension. So D is just the number of columns in X, or equivalently in Q, K, and V. And we're going to form the softmax of this. By the way, this really means here the softmax applied to each row in this matrix. I'll talk about the sizes of all this in a second. And then we're going to multiply this whole thing by V. And this operation right here, that's it. This operation here is the self-attention operation. That's the core element that sort of defines every modern AI model. Let's look into this operation a little bit more, and then we'll also actually give a quick implementation of this, because it's obviously a very central operation to all of modern AI. And so it's worth spending a little bit of time on the actual details of what this operation does. So let me go ahead and actually rewrite this operation here. Let me write the operation y equals softmax of Q, K transpose divided by square root D times V. And I want to sort of define a few more things here just to make this very explicit. So the first thing I'll say is remember kind of what this softmax is. So the softmax operation, say for just a vector x, I'll write it like this. This is just equal to the exponentiation of x. So we exponentiate every element of x, and then we divide by its sum. So we divide by the sum from j equals 1 to n, say the dimensionality of x, of the exponential of xj. So this is the softmax operation. And again, when we define it in terms of this particular this particular element here, so this particular sort of matrix here, we're talking about doing it by row. So but before we sort of get into that, as we sort of understand what that means, let's take a moment just to look at the size of this operation here, sort of what this set of multiplications is doing, and the size of each term. All right, so remember, in this setting, Q, K, and V are all T by D matrices. What this means is that this operation here, so I guess I should say this whole thing here, well, Q is a T by D matrix. K transpose would be a D by T matrix. So this whole thing here would be a T by T matrix. Maybe I'll write that out actually a little bit more explicitly. Q, remember, would be a T by D matrix. K would be a D by T matrix. D by T. And so this whole thing, of course, dividing by square root of D, that's just a scalar, so it doesn't affect the size of it. So this whole thing would be a T by T matrix. When you, this element here, of course, is also a T by D matrix. When you take the softmax operation by rows, it doesn't actually change the size, right? It just exponentiates the elements and then divides by their sum. So this whole thing here is still a T by T matrix. And then multiplying by a T by D matrix gives you, as an output, this whole thing would just itself be a T by D matrix. So self-attention takes as input, really, you can think of it as 3 different T by D matrices, but of course, really, they're all transformations of the same T by D matrix X, and outputs another T by D matrix. That's at least the most natural way to think about it. Each element here is important enough that I think it's worth kind of highlighting precisely what is happening with each one. So let's think of this now. We're going to call this whole matrix here, we're going to call this sort of softmax, without the V here, but just this whole matrix here. We're going to call this whole matrix A. And then we're going to call this, we're going to write explicitly this matrix V as now X times WV transpose. And so in doing so, I really want to highlight the fact that this softmax operation is exactly kind of different types of matrix operations, either left multiplies or right multiplies. Now, it's a little bit more subtle than that, I admit, because in fact, A itself is a function of X, right? Because, you know, each of these Q's and K's are functions of X. Q and K are both functions of X themselves. But as a whole, you can still think about this operation basically being one that multiplies on the left by some matrix, so multiplies X on the left by some matrix A. This is often called, by the way, in the context of self-attention, this term here, which is the whole softmax, is often called the attention matrix. Draw that a bit better. This is called the attention matrix. That is just the softmax. That is just this whole term here. And what this operation is doing is it is using this attention matrix to mix together the rows of X. Remember, when we multiply on the left, we are mixing together the different rows of X by the different coefficients in A, and then applies this other matrix on the right that applies this operation separately to each element of X, right? Because multiplying on the right applies a linear transformation to each row of X independently. And so what self-attention does is it really combines these two operations to mix together different elements of X. And just to sort of highlight that one more time, remember that if we have a matrix, so if we have our matrix A, I'm going to write like this, times X, and if we write our matrix A in terms of its rows, so I'm going to write A as basically some first row transpose, second row transpose, etc., all the way down to AT transpose. And each element here is, of course, also has T elements in it. We multiply this by X. Then the first row of this output would just be the operation of A1 transpose times X. And again, writing that even more explicitly, this, or he's talking about it more explicitly, this operation here would be a linear combination of the rows of X with the coefficients given by A1. And we can, of course, do the same for A2 in the next row, etc. So the important point here is that, and we highlighted this last time too, so I won't belabor this point too much, but it is important to emphasize. Each row here is a combination of all the rows of X. In other words, if we think about each row in our matrix kind of corresponding to information we have in one word of our input, then self-attention is what combines information from all those words, right? Because you don't want to just predict the output based upon each word independently. You want to somehow share information across these words to get the best prediction of the output, and self-attention is how we do that. Now, it turns out that actually self-attention winds up being the only operation that mixes together information in the rows in a transformer. Every other operation is more like this one that just applies to each row independently. All right, so self-attention is going to be how we actually mix together rows and mix together information over our input sequence. Okay, so that typically is actually how I often think about self-attention. However, it's worth mentioning that there is another interpretation which is very common, and so I'm gonna present this here. But I do think this is actually a very imperfect analogy, and so I think it's only sort of a partial explanation, and that is the soft lookup table interpretation. And this, by the way, is sort of where these names of queries, keys, and values came from. Though again, I think that in the context of how self-attention is usually used, it's a very imperfect analogy. So the analogy I'm going to use here is basically one of a Python dictionary. So we've been using Python in this course a lot, of course, so I assume everyone knows how, at least functionally, you can think of a Python dictionary, right? A Python dictionary is sort of a mapping of keys to values. And so, for example, in a Python dictionary, maybe you have the key. I'm just going to use just sort of random analogies here, or random inputs here. But maybe you have the key 1 that refers to the key A that refers to the value 1. The key, I'm actually going to give myself some more space here. There. Maybe you have the key B that corresponds to the value 5. Doesn't have to be any order to anything. And the key C, which corresponds to the value 10. Let's say you had this Python dictionary. And I'll even annotate it with kind of the Python notation. So the normal way of kind of thinking about these different terms is you would call this term, this first term here, point more clearly to that, you would call this first term the keys in the dictionary, and you would call this next set of terms the values in the dictionary. And if I were to sort of issue a command like this, say D, I'll just define this as being equal to D. If I were to say D A, then when I input sort of a key into this thing, I call this term here the query. So this is sort of the key I am looking up when I call a dictionary to sort of find a given key. The input I pass in that dictionary is the query, right? And conceptually, what a dictionary does is it just sort of scans my whole set of keys, finds the key that matches that query, and returns the value. Okay, so I'm going to write that down just because it's worth kind of emphasizing. I know this is very sort of, in some ways, a very pedantic way of describing what a dictionary does. But what a Python dictionary does conceptually is it, given a query, it scans all the keys to find a match. In the case of a Python dictionary, just an exact match to the query. Oops, let me write this down. To find a match, and returns the corresponding value. Right? And that's what a Python dictionary does, at least conceptually. Now, of course, in practice, it has a nice, for those that sort of know a little bit more about this, it doesn't actually scan through all of these things linearly. It uses what's called a hash table to do this very efficiently. But conceptually, you can think about it doing this. It sort of looks through all the keys, finds one that matches the query string or the query value. I shouldn't say value, the query object, whatever that might be, and then returns the corresponding value here. All right, so that is what a Python dictionary does. And there is a way to interpret self-attention as doing something very similar. So I'm going to, again, kind of write one more time my self-attention operation. So I'm going to write that self-attention applied to Q, K, and V is equal to softmax of Q, K transpose divided by square root D times V. And I'm actually going to look at this in terms of a single row of this output. So remember, this is a set of rows here, right? So each row contains, I'll call it this Y1, because I made this sort of Y equals to this. So this is the first row, Y1. The next row is Y2, etc. And I'm going to write actually kind of just the first row of this output and look at that kind of more specifically. So if we think about the first row of this output, well, the first row of this output is equal to, well, remember what we said, we sort of called this whole matrix here, we called this whole matrix here A. So I'll just write that again. This whole thing here is going to be equal to A of X. And what we said was this entire first row of this matrix Y is equal to, well, it's the first element of A, so I'll call that A1 transpose, times V. All right, that's the first row of this. And I'm not going to write the rest of the rows. They're all just the same thing. But what is the first row here? What is that first row actually equal to? Well, we can also, again, writing kind of the elements of Q and K individually, we could also write this first row as being equal to, so A1 here, I'll just write this explicitly here. That first row of the output of the attention matrix, that would be equal to, so A1 transpose is going to be equal to, well, it's still going to be the softmax, right? Because we still have that operation. But then the first row of the internal term here is just going to be the first row of Q times K transpose over square root of D, right? Because again, if we want to know the first row here, that would just be the first row of this matrix times this matrix. All right, so I'm going to write that out again. That whole thing is just going to be equal to the first row of Q. Maybe I'll write softmax too. Softmax of the first row of Q times, oops, yeah, I need to write that thing of transpose, times the K matrix times the V matrix. All right, and that is equal to the first row of my self-attention matrix. So let's sort of look at what this thing is doing a bit more closely. All right, so again, I'm gonna keep kind of going back to what I'm writing here, but let's look at this sort of, this operation here, the softmax of Q1 transpose times K transpose V. Well, let's write out Q here, sort of Q1. All right, so Q1 here is just the first row of my Q matrix. And that sort of looks like this. Q1 transpose times K transpose. And K transpose would be a matrix that has, I'm going to write K by, K transpose really by columns. So the first element here is K1, the next column is K2, etc., all the way up to K transpose. And so this inner product here would just be equal to every inner product of Q1 transpose times K1, Q1 transpose times K2, all the way to Q1 transpose times KT. Now, remember, the way to kind of, or one way you can think of an inner product is an inner product is in some sense computing the similarity between two different vectors. And so what we would expect is if Q1 and K1 were very similar, the vectors say were identical, then this inner product value would be very high, right? Because the inner product value is basically just, an inner product of Q and all the different key of Q1 and all the different Ks, K1, K2 to KT. And so if Q1 kind of matches that, or is the same as Ki, then that element is going to kind of be high. Whereas if Q1 and K1 are very small, then or if Q1 and Ki are very different, then that value might be very, very negative. So this is going to just be a collection. This vector here will just be a collection of numbers. And when Q1 is similar to some Ki, that term will be large and positive. And when it's dissimilar, it will be either close to 0 if they're what are called orthogonal vectors, or it'll be negative if they're in fact kind of pointing in opposite directions. So now let's consider what happens when we take the softmax of this thing. Softmax of this thing. Well, what happens here is that when you take the softmax, then elements that are large, you're exponentiating out everything in the normalizing, right? So elements that are large get close to 1, and elements that are small or negative are close to 0. So if you kind of think conceptually about maybe there is one element in this vector that's really big because it is very similar to Q1, and suppose that every other element is small, then what this approximately equals here is a vector, row vector, where most entries are 0, but one entry corresponding to the biggest element in the sort of the most similar. So this would correspond to sort of this one here would correspond to Q1 transpose Ki, where I was the most similar to Q. This would be a 1, and everything else would be close to 0. And now, when we multiply this whole thing by V, so let's multiply this whole thing by V. Hopefully I have a room here. What this is going to be is this is going to be a linear combination of the rows of V. Let me write V by row, actually, just to make this explicit. We're going to multiply this whole thing by V. So V1 transpose, V2 transpose, etc., all the way down to VT transpose. This whole thing, if we only have one element here that is 1 and the rest of the elements are all 0, then multiplying this thing by the rows of V would just be equal to VI. Well, I'll write it a little bit more. Hopefully I won't overwrite myself here. VI transpose. Okay, so in other words, what we've done in this operation is that this product here, to compute kind of the first row of the softmax, of the self-attention operator, we form this matrix here, really this vector, this row vector, which computes the similarity of the first Q term, the first query term, with every key. We take the softmax of this thing, which approximately, and again, this approximate is doing a lot of work here, which approximately puts a 1 at the location of the greatest match between Q, the query Q1, and Ki. And then we output Vi, where Vi is in fact that maximizing term. So again, if we think of the Q1 here as the query, what we're doing is we're finding the most similar key of all our collections, and we're outputting the value corresponding to that key. And that is very similar conceptually to a lookup table, right? So intuitively, I'm just going to write this here, again, kind of describing what we're doing. We're finding Ki most similar to Q1 and outputting the corresponding Vi. And that's what sort of self-attention is really doing. Maybe I'll even write the fact that this is in fact, of course, Y1 transpose is equal to this thing. Okay, and so that really is why people think of self-attention as kind of being something like a lookup table. These terms here, and again, of course, and I'll go back to the previous slide for a second. Of course, in reality, you don't just do it for one row of Q. You do it for every single row of Q. So you form this same thing for the first row. Then the next row would, of course, be the same thing. You're doing kind of a lookup, softmax of Q2 transpose K, transpose V, and then etc. So this first row, you're kind of doing a lookup of which key is most similar to Q1 and output the corresponding value. This next row, you're doing which key is most similar to Q2, output the corresponding value, etc. But in general, this is kind of this soft lookup interpretation of the self-attention operation. And that's also where these seemingly kind of random designations of queries, keys, and values actually come from. Okay, so that is kind of the details of self-attention. Let me now actually go ahead and provide sort of a simple implementation of what this looks like in code. All right, so we're going to switch over to code for a moment. And I'm going to just define a simple self-attention operation. So I'm going to start by importing torch. I'm also going to actually import math. And the sort of the nice thing about self-attention is that despite, seemingly, and I guess I'll go back here for a second, despite, a lot of, I'm kind of writing out a lot of math here, there seems to be a lot going on. The actual implementation of self-attention, because it has this sort of simple matrix form here, the actual implementation of self-attention is very, very short. And in particular, it just looks like the following. So let's define a self-attention function. So let's define self-attention as a function of q, k, and v. And all we're going to do is we're going to first, let's first actually just set d, just so we have a little bit of a nicer conventions here. Let's set this to be the trailing dimension of q, right? That's going to be, of course, be d. And then all we're going to do with self-attention is we're going to return the softmax function, so torch.softmax, applied to q times k transpose. And actually, softmax requires that we specify a dimension for the softmax operation. So we're going to form this, we're going to kind of compute this softmax again over the last dimension. So this is going to be over the different rows of our matrix. But we also, before we do that, have to divide by d. By the way, I think forgetting to divide by d is the #1 mistake I've ever made. We can talk about why this is necessary too. In general, we of course could kind of fold this d term into the q and k, the wq and wk matrices, but so that they have kind of, because we want to have sort of more normal initialization of these, it's a little bit more common to fold them in here. And then we're going to have this separate term here. And then we're going to multiply this all by v. Okay? So that's our self-attention. Actually, that's it. This is the entire sort of operation that kind of underlies, again, most modern machine learning, most modern AI systems. So let's see what this looks like in practice. Let's define x to be just a random matrix that is our sequence length, which is say 1,000 and 100, say, and we'll say d, which is 10. And in this case, we're going to form wq to be a random matrix, which would be in this case then 10 by 10. And we'll do the same thing for wk, wk and wv. Right. Now, in doing so, after we've done so, we're going to, again, these are not how real matrices would be scaled in this sort of setting, but we still kind of want to write them this way. We're just doing this for sort of illustration purposes. I can now set q, k, and v just be equal to the transformations of x according to these different things. So wq transpose x times wk transpose and x times wv transpose. And then I can set y to be equal to self-attention of q, k, and v. And that is my self-attention operation. And if you look at the shape of y, we'll see that y, just like x, is also a 10 by 100 matrix. All right, so that's actually kind of, in some sense, all there is to implementing self-attention. There's one more little subtle point that I'll make here, which is that in reality, you often want to apply this operation to a whole mini batch of examples. And in the case of when we're representing a structured input, we already have sort of each input being a matrix. So we need one more dimension to start, which is the actual mini batch dimension. So I'll say this is 5. And if we just did this like it was, actually, something would break here. And that breaks here in this line here, because you can't apply this simple transpose operator, the .t operator transpose a tensor if it's not a two-dimensional tensor, i.e. a matrix. So when you have a larger set of dimensions, you actually need to explicitly transpose the last two. dimensions to make this really a batch matrix multiplication. So this is how you would actually implement self-attention, and now that will work both for the case where X is a batch of examples and for the case where X is a single example. So it will still work in this case, but in this case now, Y ends up being another tensor that's the same size as X, just with this mini batch in the first dimension. Okay, let me switch back now, and that actually is the entirety of what you need to know about self-attention. Let me switch back now and just highlight a few last things. And I am going to go back to this slide here. And one thing I actually realized now that I was doing is I did forget to put the avoid putting the dividing by square root of d just for the sake of it. It gets a little bit cumbersome to write it each time, but of course in reality each of these would be divided by root d here. So this would be divided by root d, etc. And also here, of course, this would be really divided by root d, but that's just a scaling. I should mention something about this scaling. So it might seem odd that we are dividing by root d here, because after all, both q and k are just functions of x. So we could just sort of fold that d into the q and k matrices, but it's just a little bit more convenient not to. When we do this, and let me go back one more slide. When we do this, so when we include this division by root d, this lets us actually use more standard initializations for WQ and WK. We end up being able to use the exact same initialization we use kind of for normal linear layers. And this just actually has to do with the scaling. Because here we're multiplying sort of terms that involve this term and this term together, it winds up being a little bit less convenient to have these each be separate, be differently scaled terms, right? This one and this one. And so it's valuable to have this division by root d. Okay, so this is actually almost all we need to know about self-attention. And we are now going to talk about a few, before we sort of finally get to multi-head attention, we're going to talk about a few properties of self-attention. And in this case, what we're going to do is we're going to talk about two properties of self-attention in particular. We're going to talk about, number one, the fact that self-attention is invariant. I'm going to use a different word there, but actually, I'm not going to use the word invariant. I'm going to use the word that self-attention doesn't really, in self-attention, it is sort of, it doesn't matter how we order the rows of X. All right, so it doesn't actually really matter in which order the rows are. And what I mean by that is if we have our matrix X and we shuffle the rows. So again, here, let's suppose that X is equal to the first row, the second row, etc. And let's consider sort of a alternative version of X where the rows are all sort of mixed together. So maybe the first row actually is X100, the next row is X 150, etc., all the way down to, I don't know, X5, say, is the last row. So this is just some reordering of the rows of X. Well, if Y equals self-attention applied to X, And really here, I mean, of course, self-attention applied to all the different, self-attention applied to the Q, K, and V formed by X. Then in this case, we have actually Y prime, or rather, if we form sort of Y as being a function of self-attention applied to X, and we form Y prime being self-attention applied to X prime, then in this case, this and this term equals Y1 being the first row, etc. Then this term here, so the self-attention we get when we apply it to X prime, that would just be equal to, well, in this case it would be Y100 transpose, then Y transpose 150, etc. Y5 transpose, that's just the same as where these indices are the same as these indices. In other words, if I take a matrix X and I scramble up all the rows and I apply self-attention to it, that is just equal to the original self-attention sort of scrambled up according to the same scrambling of the rows. The easiest way to see this, I mean, I can prove this mathematically, but the easiest way to see this is just sort of via code. So I'm going to form some what's called a permutation. So this is going to be a permutation. To make it simple, I'm going to go back to this case here. So a single batch case. I'm going to form what's called a random permutation of 100 elements. And if I do this, this is just going to mix up the rows of X corresponding to this permutation. So here I can look at what P is. So P is just a ordering of the numbers. So the first row will be the 11th row, the second row will be the 93rd row, etc. Of X. And what we can see here is, so maybe I'll set X underscore equal to this. And if we form self-attention on these, so we first form self-attention there, and then we form self-attention on this new set of Q's, K's, and V's, then it turns out that our original self-attention, if we permute it, this will be equal to sort of our new self-attention. All right, and these are actually all zero. They're just close to zero numerically. And we can look at this even by saying this thing, norm, is very small. That's effectively zero rounded off in floating point arithmetic. So conceptually what that means is that self-attention should be thought of kind of as a set operation. It's given a set of inputs where each element corresponds to a different row of the matrix. Basically what's happening is that it is applying an operation which applies to this whole set, and if you permute the elements of the set, you will get the same output just with those elements permuted. In other words, the ordering doesn't really matter for self-attention, and so you should think of it as applying to a set of inputs rather than sort of a specifically ordered collection of inputs. Now, that's a nice property of self-attention, but it's a bit odd in another sense, because we know, of course, that for language models, the ordering of words does matter. And what this is saying effectively is that self-attention is an operation that doesn't pay attention to the order of the inputs, i.e. the order of the words in the input to our model, which is a bit sort of unsatisfying because, after all, order does matter. And so the way we're going to talk about this a lot more next time, because this is when we'll talk about kind of the application of self-attention in a transformer architecture to language models. But we're going to talk more about how we kind of fix this problem in language models, which is through a technique called positional encodings, or more generally, different types of positional embeddings. And we'll talk about what that means next time. The next property of transformers that is sort of important to mention here is that every output, so every output row can depend on every input row, right? Because we have this matrix, AX times X, or times V, but times X, WV. And as long as the matrix A is a full matrix, right? Every element here can in fact be non-zero. And what this means is that the mixing of our elements of X, in this mixing, every output can depend on every row of the input. So in other words, this is sort of a full mixing over the rows. And this is also a very nice property, actually, kind of from a representational standpoint. There's a lot of other kind of sequence methods where this is not true. So for example, in convolutional networks, this is not true. Every output row only depends on a small subset of the inputs. The nice thing about self-attention in some sense is precisely this property, that it can sort of mix between inputs that are very far away in some sense, as long as they are close kind of in the sense of this kind of soft lookup table. The problem, though, which we'll also see here, is that for language models, this actually means that it would have the ability to predict past words from future words, which is not something you want in a language model. And so we're also going to have to fix this property in self-attention for language models, which we'll talk about next time when we talk about masked self-attention. So again, these will both be covered next time, but I just want to highlight these facts because these are masked self-attention, because these are both very foundational properties of self-attention, yet this sort of what's called invariance or equivariance, more precisely, to reordering of the terms. And then also this notion that every output depends on every row in the input, which, while desirable maybe in general, is not desirable in the specific case of a language model, and so this also has to be fixed, and it's fixed using using masking techniques. Okay, so those are actually the two properties of self-attention that I want to highlight here. And now, before we end for today, we're just going to talk about the last aspect of self-attention, which is an extension to self-attention that is often called multi-head self-attention, or just, in fact, multi-head attention. And the motivation here is that self-attention is a very sort of powerful, let me form a straight line there. Self-attention is a very powerful operation. But if you look at kind of the default way that I wrote self-attention, in particular, so when I wrote self-attention before, I had this matrix A times X, A of X times V, or more exactly, A of X, X, WV. And in our mixing here, so in our mixing, kind of A1 transpose times X, which is equal to A1 transpose X, A2 transpose X, etc. In this mixing, the mixing coefficients, so the terms that mix together the rows of X, are the same for every single kind of column of X, right? So we're mixing together all the rows of X, but these mixings all have the exact same coefficients. So we're using the same mixing coefficients over this whole matrix X. And while that's conceptually fine, or put another way, there's sort of one single kind of soft lookup table that you're applying to all the entire query, the entire key, and then all the values. And while that's kind of fine, it does wind up being the case that this is not very representationally expressive. Ideally, we would actually want different components of the output to potentially be mixed together in different ways. So even in the first row, we might want the first set of elements, the first, say, n elements in the row here to have one mixing. The next elements could have some other mixing, etc. And so what we're going to do, and this is sort of we would like to have this sort of a richer representation in this case, and this is exactly what an operation called multi-head attention does. So what multi-head attention does is actually very simple. Multi-head attention, basically, instead of running just a single self-attention operation, it actually runs several different self-attention operations and then combines them back together. So let me just define kind of what I mean by that. So multi-head attention sort of proceeds in a few different steps. The first step is we're going to form the same kind of Q, K, V as before. So Q is going to equal X, W, Q. K is going to equal X, W, K. And V is going to equal X, W, V. And then, in the second step, we're going to partition each QKV by columns into H different groups called heads. All right, and what I mean by this is we're going to take our matrix Q and we're going to partition it into H different blocks. QH is an H. And we're going to do the same for K and V. So same for K and V. And so same for K and V. All right, and each block here, so each block QI is going to be, of course, a matrix QI. It's going to be a matrix which still has T dimensions. Still has T rows, really. But the number of columns is no longer D. It's now D divided by H. Right? Because we've partitioned the columns of Q, or partitioned Q by column, into H different blocks. So each of these has the dimension of our original dimension D divided by H. And all we're going to do, and the same for K and V. So K would also be partitioned like this into blocks that are this same size. And so I'll just write this also that, Q, V, QI. Oh man, copied the little hat of the I there. QI, didn't even get enough of a movement. So QI, KI, and VI are all this size. So we're sort of partitioning all of them by columns into these different blocks. And what we're going to do then is that we're going to define multi-head attention to have the output just be self-attention applied independently to each of these blocks. So Y would be equal to, well, the first block would be self-attention applied to Q1, K1, and V1. And that's the first block, and that block itself would, of course, be the same size, because when we apply self-attention, it ends up being the same size. So this would be a T by D over H block. The next block would be sort of the same thing for 2, and I'll just write the last block here, would be self-attention applied to Q, H, K, H, and V, H. And that's this next block. And so when you do this, when you combine these all together, of course, Y as a whole is still a matrix that is T by D. But instead of just sort of one self-attention operator, you're now getting H different self-attention operators. And so what that means is that this block can have one set of ways of mixing together the elements of V. This block has another way of mixing together the elements of V, etc. And this gives more expressive power. Now, one last thing is that there usually is one more operation at the very end called a projection. So we multiply by one more set of weights here, where this last set of weights, this is just by convention, of course, this could be a separate linear layer. This is called the weight projections, the projection weights, and this is just also a D by D matrix. Okay, so now actually, because each of these operations kind of applies independently to just its group, you want to mix kind of all the columns again together of everything to sort of share information across all of these. So you typically apply one more matrix WP at the very end. But this is the actual operation that is used in most large language models. And really, once you know this and once you're familiar with this and you'll implement it on your homework, you will be able to implement really all the aspects of a large language model. Okay, so that's actually all for today. Next lecture, we're going to talk about how we integrate self-attention into a few more operations to form what we call the transformer architecture. So I'll see everyone next time.